Welcome back. So today I continue. I will talk a little bit. I will start to talk about the A-side moduli. I will rephrase this matching of cycles I described yesterday. This is, this is not this is conjectural, but you can check in example. Can check in examples. Then I will talk about some examples, and then I want to start to show you the enumerative, get a glimpse of the invariance we're going to see, glimpse of enumerative invariance. And so this will involve open covariant invariance, closed covariant invariance, and a lot of things in between. Then tomorrow I will run IMS. So I'm going to be directed tomorrow, right? for YD, where Y is Fano and D is smooth anticanonical. Really, I'm mainly going to be looking at Delpatzer surfaces, but I'll make some more general comments. And then on Sunday, so I will tell you how it works. I will give you some structural results, you can find some superpotential, etc. And then Sunday, I will prove the enumerative correspondences, prove various enumerative correspondences between. So there'll be different results. One result is going to be this period integral computes your maximal tangency locomotive invariant. Another result will be the invariance of the pair y, d are equivalent to the invariance of D up to some coordinate change, which is very natural in the context of intrinsic mirror symmetry, and other results like this. But anyways, now let's just recap. So yesterday I hope I could give you some, convince you that it's really interesting to look at things like this. So we have families, maybe over small disks, maybe over small balls, maybe, maybe something like this. Actually, let me just put a small ball. It will have some zero fiber over 0. We may want to have these families to have different properties. So in general, you would want it to be flat, but then maybe you need some modifications such that this object is log smooth. And then given that, if you apply, so what Julia was telling us, if this is log smooth, then you can take its tropicalization. So I will also review this tomorrow, but for now you could just take the definition that Julia was giving yesterday. So if this is log smooth, and here you can already see there's a bit of a dictionary, because to make this log smooth you may need to impose some blowups, and then that could make the geometry a bit complicated. So we saw an example of this yesterday. Now. What about tropicalization of subvarieties? So you could imagine that you have some subvarieties V inside here, and then it could be the case that if you take V and V0 with the maybe induced log structure, so induced log structure, then you can take the tropicalization of this, and then it will have some nice map here. I'm writing this not as a claim. This is just the sort of strategy you would want to adopt. And if V is relative dimension 1, so if V is relative dimension 1, so relative dimension 1, then this implies that this gives tropical curves. Yeah, and then if you have, which we know from Julia's talk. Now there's also a variation of this where you could ask about not having curves but having cycles, and then so to get getting tropical 1 cycles, so tropical 1 cycles. So this is established in the work of Rudert and Siebert. And they also show that so this is a right. When I say cycle, I mean you have to like relax. You're not looking at right. It's the analogy is you have a curve and you have its homology class, right? So by cycles we mean we want to look at some homology classes and say they do this, and they show that so if you have the integral over some tropical, I mean so you and then they show that you can lift to Lagrangians in mirror family, and then let's say this Lagrangians is L, and then the integral of L over the homomorphic volume form. These give canonical coordinates. Yeah. So then that's where you get this idea that maybe so the like the hope or the dream or expectation. So more generally, get so families like this, V corresponding to I don't know some cycles L. And J of V equals I of L, where this is, I'm going to introduce this in a second. This is component of the J function, and this is a period integral. And moreover, and hope, so moreover, you would want to have some like SYZ picture like this, where this is a fibration in S1 to the n minus k, if L was in H n minus kk, and then here V should be in HKK of the mirrors. Yeah, so I jumped a bit ahead of the way I plan to structure this, but that's okay. So here we would put X check, and here we would put X. So that's kind of the motivation, yeah. There's maybe one more point you can make about this, which is that you actually find, so if you see the book of Cox and Katz, you can really find, maybe I'll put it over there. So if you look at their book and you read the relevant section, you can really see that. So Cox and Katz. So you can really there is a basis of Hn of the mirror as Z coefficient such that actually, maybe I'll phrase this later. That has like the right properties that has the right weight filtration with respect to periods. So what do I mean? I mean that we really have, we really will have, on some end we have the SYZ fiber, at the other end we have some Lagrangian sections. Then at the next level we'll have these gamma i's, which give, these are the let's call this gamma, these gamma i's, and then we'll have a bunch of other things, and then this, the integral of this gives 1, the integral of this gives the coordinates, and then everything here else here, so this is like some SYZ section, and everything here everything here should give you some enumerative information. And moreover, there's like a nice pairing, these pair to 1, and then you have like like the respective components will have like a Poincare pairing. Okay, so I skipped a little bit ahead, so let's go back to writing definitions. And so I will kind of describe how this works in some examples, but you're welcome to learn. You're welcome to. Actually, it's a great idea to try to look at some examples and try to make this work. And the examples I will talk about are like based on work by Quacquay, Pomigliano, and Ueda, where you can like kind of see this. You can see this structure appearing, but it's for toric-Calabi-Yau threefold, so it's not a. This is for compact. This is a compact case. So I don't have a like general statement. All right. Any questions so far? Okay. Great. So let's go to the symplectic side. So the other side, the A side. So X, which was compact Calabi-Yau. I mean, I'm talking about compact Calabi-Yau, but later I will look at log Calabi-Yau varieties, but that serves as kind of inspiration, because the reason we do log Calabi-Yau or like toric Calabi-Yau is because the general case is just too hard. Yeah. So we have a Kähler cone. So this is a Kähler cone. So it's inside H. You could so you take H 1 of X, and then you intersect it. Actually, we don't. Sorry, maybe. I hope I'm not doing something weird. X R, and then you tensor with. Well, you take generators. Okay, yeah. So Kähler cone, which is generated by elements of Kähler classes, generated by Kähler classes. H11 X, and then maybe here I put Z. Yeah. So I take the cone generated by Kähler classes. This is a cone inside H2. Now we already see a problem, which is that if you wanted to compare this with the complex moduli on the other side, this has the wrong dimension. So we're going to look at the complexified Kähler moduli. So we're going to complexified Kähler moduli, which means we're going to add we're going to look at expressions of the form exponential of omega plus IB, where omega is in the Kähler cone and B is in H2XR. So this has dimension. Okay. So if you want to go further, you might want to quotient out by automorphisms. We're not doing this. That makes it way too hard. Anyways, so the dimension is H11 of X by construction, and these are always canonical coordinates. So we use, in general, so we will use, so write tau equals log t times omega as an element inside mk. X, maybe omega we take inside H11, but with integer classes. So we take one of the lattice points that generated, and then we multiply by log t. So that then gives you, if you just plug this in, you can see that this gives you a good expression, and then you get canonical coordinates.
Do you want the greater large and then becomes 0?
Please ask again.
Do you want large volume to correspond to 0?
So you're saying I should put a minus? Yeah. So the answer is yes, and yesterday I told you that at some point I will start using. That's right. So yesterday I introduced that 2 pi I is equal to 1, and today I'm introducing that minus 1 equals 1. Okay, but you're of course right. So I should probably put I should put a minus. That's what you mean, right? Yeah. But yeah, so I'm being a bit sloppy with this. And so the reason is because if you take t a coordinate in C star as t goes to 0, then that will go to minus infinity, and then you want it to go to like a large volume, right? Anyways, so these are canonical coordinates. I'm also identifying plus infinity with minus infinity. I'm just kidding, of course. It's important to be precise. All right, and so these are canonical coordinates by construction. So these are our canonical coordinates. So remember when we were talking about canonical coordinates yesterday, we were doing something like, let me see, how do I want it? Write it? Yeah, we were doing something like t to the yesterday we were doing something like exponential, then you have we declare them to be canonical coordinates. Declare to be canonical coordinates. We're using our power of making definitions. And this is really by construction the case, because if you just put in log t or minus log t times omega, and then you integrate this over some curve class, which will be the corresponding integral that you might want to be doing. So you integrate this over some curve class, so C in H2, curve, or just some curve. Yeah, you can just integrate it with some curve, or curve class, doesn't matter. And you take the exponential of this, then by using your very complicated mathematics, you see that this is the same as the integral t to the integral of c omega. And now this is an element in N, because if this is an effective curve class, so this is well, C is really a curve. Then this is because we're integrating a integral Kähler class, right? We took it to be integral, so over some actual curve. So because Kähler classes correspond to ample line bundles, that's going to be a positive number, but it's actually going to be an integer because everything is in a lattice. And then there's also a -1 that should come, I think, here maybe. But that's why I don't, that maybe here. And then that's exactly the statement we had on the B side yesterday. This is the analogous statement, analogous analogous to B-side definition. Yep. On the B side, we were integrating middle dimensional homologies. We were integrating the holomorphic volume form over middle dimensional cycles. Here we're integrating a Kähler class over curves, and they satisfy the same relationship. And we declared that relationship to be canonical. We define coordinates that satisfy this relationship to be canonical coordinates. All right. Now, given this, are there any questions? There's a lot of like details maybe one could write, but I'm not, because I don't want. It would take a long time, and maybe you're not too excited about reading things that are written in a book from the 90s. All right. So now, if you take the flat sections of the quantum connection, flat sections of quantum connection. So that's actually that's something that is studied a lot still nowadays. For example, I think Pomerlano has some work about this. Maybe he will talk about this next week. I'm not. So what is a quantum connection? So you take you start with H2, and then you take the trivial line bundle given by cohomology, and then you have a quantum connection you can look at for flat sections, and these give you the J function of given tau. So you have to like cap them. You have to pair them with some elements, but then you get given tau J function. J function. So let me introduce this. So we need some basis. So we take T an integer basis. Well, it doesn't matter. Maybe it matters. So we want them. We take. So A is an index. J is going to keep track of codimension, and if you invert the indices, then J is going to keep track of the dimension. Yeah. And then you want them to be dual in the sense that you want, if you pair TJA cup product with TBK, this should always be 0 unless J is equal to K and A equals to B. So this being the Kronecker symbol. I had when I learned linear algebra, that was ages ago, our teacher introduced the Kronecker symbol by saying that poor Kronecker, he had such an important contribution for mathematics and is remembered by this trivial symbol. All right.
2n minus 2j.
2n minus 2j, yes, thank you. Thank you. I'm also setting 2 to be 1.
You don't write complex numbers, only much points.
Exactly, yeah. Yeah. All right. Now, yeah. Everything is equal. This is a theory about everything is equal, and then you slowly make it unequal. Okay, and then so I'll write the J function on the next board, but maybe just I introduce some notation first, which is so we're gonna like choose as a Kähler parameter. So there will be a parameter. So this is a connection on H2. So we'll parameterize an element in H2 or Kähler element as here. So we're gonna like write tau equals. I'm probably gonna just forget about the minus. In the Kähler-Kohn, in the complexified Kähler moduli, and then I know I should keep track of the minus, but and then we're going to use this expression that QW divided by Z is E to the log Q omega divided by Z, which is 1 plus, so now I can write this as 1 plus log q omega divided by z plus log square q omega square divided by 2z plus da da da. And so this is an element in homology of x with complex coefficients. But then I also have to adjoin log of q, and I also have to adjoin 1 over z. I will also adjoin q, but I don't have to do this. Well, I will do it. So q is a power series term, as we will see in a second. Okay, so that's just notation, and then the j function is defined as follows. So we're going to write, the j function is going to depend on this parameter that we've chosen, which is which is log q omega. It will depend on some other parameter z, which is not so important for today, or at all, and we will be able to write it as a sum of terms. So this is going to be a cohomology valued function. We will have to add log of q. We have to add 1 over z. And then, but we also have to add a parameter, a Novikov parameter. And then it will be, it will have different terms according to our basis. So t to the ja log q omega z times t to the aj. So there are different ways of writing the j function. Now you take one of those ways, and then you use this basis of cohomology that you have, and then you get this nice expression where the terms ja log q omega z are given by, so there's some I don't know, classical term, or holomorphic term, so this is something classical, plus, and then we have the quantum deformation, which is given by summing over curve classes. And also positive integers. And then you have Q keeps track of the curve class as paired with omega, right? So we use our Kähler class to determine a degree. And then you have the genus zero Gromov-Witten invariance, which I'm writing down here. So you may have some psi class, which you have this like sum over here, and then some insertions, Taj, and then this is genus 0, 1 marked point, x, and so this is a genus 0, so genus 0 Gromov-Witten invariant of x. These are psi classes, and this is the first Chern class of the cotangent bundle. And then as insertions, we take TA to the J. Now, that could be in the wrong, so the way we define this, you have a virtual fundamental class and then you impose some conditions. Now, if you just have this one, you might be in the wrong virtual dimension. So what these terms do is they bring you in the right dimension, right? So this is, to get correct dimension or virtual dimension. I don't want to like talk too much about J functions because it's always a bit messy. But I just want to say that there are solutions to the quantum connection. You can write them in this nice way where you decompose it into terms, yeah, and then each term has an enumerative interpretation of all the ways of counting. So this is this is degree beta as well. This is, you can think of you summing. This is we sum over all the ways. So you can map all the ways you can map P1 into X with meeting subvarieties. So the terms of the subvarieties will be something omega to the k times t a j, and then fixing complex structure of the base curves. Complex structure of curve. I mean, this is just a way. This is a vague definition. But maybe that will be enough. So the psi classes have the effect of fixing the complex structure. This has the effect of you adding these powers of omega, but also you're keeping track of some log term, and then you have an insertion and you have an invariant. Yeah?
So how is Q and T related?
Yes, so Q is equal to T. That's another one. Yeah. So where did I write T?
Log T omega.
Yeah. So yes, exactly. So Q is equal to T. Yeah. It's all the numbers are equal to each other. Yeah. I should. Yeah. So I have. I in my notes I changed between Q and T. So but absolutely, this is very important. Yeah. We also declared that Q was equal to T. At the end of the week. There are no more letters left in the alphabet. Yeah, so just to recap, so this is kind of a universal generating function that counts all the ways of mapping P1 into X with meeting all possible subvarieties. And I don't want to get into more details than that. All right, and then the prediction of mirror symmetry becomes becomes the following. So the prediction. No, maybe I think so the prediction of mirror symmetry of string theory, or let me call this enumerative mirror symmetry. So enumerative mirror symmetry. Mirror symmetry. So this is EMS. So we have, Calabi-Yaos come in pairs. X versus X check. On one side, you vary the Kähler parameter. So how did I write it? So yeah, you take tau in the Kähler, complexified Kähler moduli, and around some tau 0, which is the large volume limit. So this is where that's where it's important to have a minus log t. On the other side, we have x. So this one. Now I'm going to switch to writing this as log t omega. You know, my strategy is I confuse you with indices so you don't realize the other things I'm doing. So I'm going to call this t, and then t is inside the complexified. Inside the complex moduli. X check, and this should be around the mum point. T0. And here's the key is, or one of the keys is we have to match them. We have to match so we have a mirror map. So mirror map matches log t omega with t. So you can think about, so omega corresponds to a, so omega here is a choice of Kähler class. And then on the other side, that will be a choice of one parameter subfamily, right? So you can see that this is a comment that Pierrick made yesterday, which is if you like a choice of a Kähler class on one side, a choice of a line bundle on one side corresponds to like a choice of deformation on the other side. And then, so that's what, you know, this aspect is really, in general, this is tricky, and it leads to corrections. And see the example of yesterday, see example of the elliptic curves. So yesterday I gave you this example of a family of elliptic curves, and I told you how to get canonical parameters. So really what I was doing is I was telling you how to get the mirror map. And that was not easy, right? I had to solve compute some period integrals, etc., etc. That part is not easy. And that's why, you know, so one of the you know, like, so this part, this trickiness is solved by using IMS. So you can either look at papers that were written by IMS and then do the corresponding modifications, or in intrinsic mirror symmetry, this mirror map is already part of it's part of the construction. Yeah. So no mirror map in IMS. So you know in some sense the original construction is you want to vary both sides. You find some nice parameters and then you match them, but that creates some problems. So we really want to avoid it. Okay, but the next thing you can do is you have a on one side you have an A model variation problem. On the B side you have a B model variation. You can describe this like here you'll have some quantum connection. Here on the other side you have just Gauss-Manin connection. Like there's like a very like there's a lot of things you can say. Here you also have some quantum differential equation. Here you have some Picard-Fuchs equation. There's a lot that can be said, but then the solutions of these variation problems should be matched. And so here we have the solution here is given by the J function of x, or maybe maybe put it this way: J function of x in log t omega. I'm just going to put z equals 1. So the z, if you Here I'm missing a z divided by m, but a z is just some coordinate that keeps track of psi classes and psi classes and how many times you applied the Kähler class. But that's the next thing we're going to set to be 1 because it's not so relevant for today. So there's a solution here, and there's a solution here, which is the given tau I function in t. And now the famed given tau theorem is that they're equal. Oh, x check, absolutely. Thank you. Yeah, thank you. X is equal to x check. That's right. I'll have to think about more things to set equal. So given tau mirror theorem tells us that so j of x equals I of x check. Yeah. So there are many ways of formulating this theorem. So the way, it is formulating given tau mirror symmetry is he defines a j function the way I did. He defines a I function using some hypergeometric series, some like modifications, and then he shows that both live on the symplectic cone, and moreover that there's only one function, like there's only one function that's supported on the symplectic cone, and then that means they have to be equal after some change of variable. So the way I'm phrasing it here is just really so the way I'm phrasing it here, that function should have, you know, for me, this function has its component. Well, let me put it this way. Yeah, so like refinement of this would be that this one equals, if you fix some t taj, it should be the same as I if you fix some L that corresponds to it. Okay, maybe I should rewrite this up here. So that's the.
It's not a refinement, it's just a package.
It's a repackaging. Yeah, that's right. You're right. Yeah, it's a repackaging. That's just yeah. So let me. Yeah. So this statement is immediately. I mean, it is. You will have it. So Taj of x equals I x check of some maybe Laj. Let me just call it this way. Where by this I mean the period integral over Laj omega t on x check, and where this one is the corresponding term of the I function, where Taj corresponds to Laj. So you can always refine it in this way, but the claim is that there should also be some like geometry that relates the two. Yeah. So there should also be, and there should be, so and related by SYZ. And maybe I should say topologically. So this refinement is okay, but this is conjectural, like. But you can check in examples. And one reason this is conjectural is, of course, because SYZ is conjectural, right? But that's kind of the statement we're looking for. Yeah. Questions?
Regarding the miracle, given house miracle, you want to cause some comments on the others as we did?
Okay, yeah, absolutely. So absolutely. So we also have, so this is Yao, Liang, and Li and Liu. Yeah.
L-I-A-N, yeah. L-I-A-N and Liu, yeah. Not Liu, yeah, and no Liu.
Sorry. Yeah. Yeah. I told you all the letters are equivalent, and in particular, one letter is equivalent to no letter. That's right. So there are various versions to like phrase the mirror theorem, and then in some sense, one theorem which is proven by Yao, Liang, and Liu was where you look at so in the case of like quintic threefolds, you look at invariants that come from invariance of the P4. So you want to kind of like restrict, like you start with mapping P1 to P4, and then you want to look at which ones actually map inside of your quintic threefold. And then that's actually, that description is very close to the definition of the twisted I function, and then he gets, so they prove the same theorems. In fact, I should say that my approach is closer to the approach of Liang and Liu, and in particular, later when I will talk about how to relate mirror symmetry for Y, D, and D, this will be very reminiscent of their work. Yeah, absolutely. Thank you. More comments, questions? Fantastic. Yeah, yeah, and then then yeah. So the yeah, and so right. So the conjecture here, as I said several times, is you should have some SYZ kind of family like this, where this one is tropicalization, this is SYZ base, and then this one is like moment map. Okay, I realize this is, you can't read this, but that's maybe okay. And then this should be fibered in like S1 to the n minus k. And as a definition of tropicalization of cycles,
S1 base should be Legendre D or something?
excuse me, oh,
The base should be Legendre D?
it should be,
Legendre D. Or because your one is tropical, one is moment.
right, that's right, yeah. Yeah, right, okay, so I think what you're saying is that I could have another one, right? Are you saying that I could have the dual SYZ base and then things like this? Yeah, yeah, absolutely, absolutely. And that's very useful to keep in mind, yeah. Yeah, so we, you know, in this conjectural picture, we have two different SYZ base, which are dual to each other. And then over one of these maps should be tropicalization, and the other map should be some moment map, yeah? Yeah, absolutely, and then it's very useful to like think about this dual picture, yeah, as well, yeah. So that's what I said. And then for tropicalization, the best definition I can give you is the one I mentioned at the start of my talk, which is you have a degeneration, and then you have a subfamily that degenerates it, and you give it the induced log structure, and then you tropicalize. I don't know how good of a definition that is, but that's the only one I can tell you about. More questions? Comments? Okay. So maybe I'll end the first hour by a comment which you can take from Cox and Katz, and then in the second part I will start to talk about actually something else. So this prediction here, you can actually, reality is not too far from it. So if you look at the right section in Cox and Katz, so we could have, there should be some, so let's say there should be some, there should be some symplectic basis. So there should be some symplectic basis of X check. such that we have, let me do it for x equal Calabi-Yau-free, compact. So we should have some sections here. This is a Lagrangian SYZ section. So in this picture, you should have a Lagrangian section. We have some cycles alpha I, we have some cycles gamma I, and we have this SYZ fiber. So this is the SYZ fiber. And then this should be an element in H30. I didn't really define it, but you can define it using some weight filtrations. H21. So these are the gamma i's, give the canonical coordinates. So Ti to some Ki is the exponential of the integral over gamma I, omega t. These give these canonical coordinates. And then we have that the monodromy Ti minus the identity really sends this one to a sum of these, this one to a sum of these, or maybe Tj, and then this one to either a sum of these or 0. It's just, yeah. And then in the, so what are these? So these, and then here, so the enumerative information should lie in here, in this side, yeah? So what are they? Well, it's a bit hard to say what they are, but you can look at examples. So if you look at some work by Chan, Pomigliano, I'm slowly getting to more recent papers of IMS, and Ueda, but also there's work by Gross and Matesi. So the S, I mean, this suggests that the alpha I are, so this is for toric Calabi-Yau. Calabi-Yau-free. These are like some S-frees, some Lagrangian S-frees. Yeah. So if you do the toric Calabi-Yau-free setting, I mean the Lagrangian section, I think is just topologically retracts maybe. Yeah.
Alpha I, we did an equal 2, right?
That's right. Yeah.
So L is the section.
Sorry.
L is the section.
L should, that's right. L should be some section. Yeah.
L is like a sphere.
Oh yeah, I think you're right. Yeah. I think you're right. Yes. Sorry. Yeah. So the toric case. Yeah. So yeah. So if you read Katz, you can see this in the compact case. Like he describes how this should work. I mean, he doesn't describe in detail, but then what I'm doing is I just read this chapter, and I'm like, that's a good intuition, and then I read their paper, and I'm like, that's the one I want. So in their paper, we have some S-frees which are Lagrangians. That S-free is not the section. Yeah, not the section. Sorry. Yeah, this is not. Yeah, not section. Definitely not. Yeah, it's not a section. And then yeah, thank you. And then so this suggests to integrate over these S-frees in the mirror family, and then see if this gives, see if we get GW of local Calabi-Yau-free. Yeah. And yes. So this is what I'll start doing in the next hour. So somehow it's a process of like working yourself up. So if you integrate over this one, you get just 1 or 2 pi. Yeah. If you integrate over this one, you just get the coordinates, right? So the integral over f is just 1 or 2 pi I to the n. But those are the same thing. The integral over these ones give you the coordinates. So the next ones should give you the invariance. And then if you did this, right, if you had some Calabi-Yau n, well, then it's going to be much more complicated, right? Then you're going to have like a lot more, but we kind of want to like work ourselves up slowly, because as I said, these integrals are done by Rudert and Siebert. This we all know how to do, so we want to like slowly go up, and because it's way too hard, it's just way too hard to look at Calabi-Yau, compact Calabi-Yaus. So we're gonna look at these toy Calabi-Yau frees. But in fact, I should say that the first step is gonna be to reduce to y comma d. And then we're in business. Like in some sense, we're a bit cheating, because we go down to dimension 2, because then we know how to do it. But then the advantage is it's going to like work more generally. Okay, so the next hour I will actually review what Pierrick was telling us yesterday, and I will use it to justify how we can reduce to pairs like this. And this is going to be a wonderful way of checking whether I understand the paper by Pierrick, Julia, and Valerie. since yeah. All right. More questions or?